Hello everyone, today I'd like to discuss another periodic trends on the periodic table for elements, and this time we're going to discuss about ionization energy. As you can see, this is the modern periodic table, organized very nicely into groups, vertical columns called groups of families. There's about 18 of them, and periods. There are about 7 periods. There's horizontal rows, and we discussed it before. The groups of families are arranged according to similarity in chemical properties. And also they are quite tied into the electron configuration. And now we're going to our previous section was discussed about the trends in atomic radius or / ionic radius. When we referring to those elements, the general trends are from top to bottom for each family or group, the atomic radius increases, and across the periods, the atomic radius decreases. And now we're going to looking at how is that going to be related to the ionization energy. So the first thing we have to define, what do I mean, that term called ionization energy. And the second, we're going to looking at the correlation between ionization energy and atomic or / ionic radius. So right now I like to kind of switch mode a little bit, and let's go into the silent movie mode. I will show you about 2-minute animation sequence. Hopefully you will explain and the concept about ionizing an element, and subsequently the definition of ionization energy and the correlation between the ionization energy and the size of the atom or the ion. Hopefully it worked, and you can actually pause and rewind for that animation sequence to truly get the definition of ionization energy, that will be the amount of the energy it takes to get the electron bonded to the nucleus away and to become a free electron. And in the general correlation between the size and ionization energy, as the size is getting smaller, which means the valence electrons is getting closer to the nucleus, you will take more energy to plug it out, and hence the higher ionization energy. You've seen those plots in the previous section about the trends in atomic radius. As you move for group 1, you go from the top of the family down to the bottom of the family. The atomic radius increases, applies to all the groups. This is primarily due to the effect number 1 dominating the number of rings, number of principal energy level increases. So if you actually plot it across the periods, as you can see here, this is the first period, second period, third period, and fourth period on the periodic table. You can see as we move from the left to the right of the period, the atomic radius decreases. This is due to the fact we do not have effect number 1. Effect number 2 is going to dominate as you are moving from left to right across the same row. The number of proton increases is actually going to shrink the atomic radius. So now you have this general trend, as we also discussed about the correlation between the ionization energy and the size, atomic radius. So you can arrive at from top to the bottom. From top to the bottom for each family or groups, the size increases and the first ionization energy decreases. And you move across the period. The size of the element decreases, hence the first ionization energy increases. So you can draw this logical conclusion. Now let's take a look at it. Is that the case? So we can actually pull out this interactive periodic table and show in the previous podcast. This is a very, very useful one. Click on the tab about the properties. Highlight this first ionization energy. This gives you the value for this particular element. This is now the iron. The first ionization energy, the energy it takes away the first valence electron. On this element will be 762.5 kilojoules per mole. So now actually we can take a look at it. If we highlight hydrogen, you have about 1312. Move down to lithium, drop down to 520, 495 for sodium, 418, 419 for potassium, and rubidium 403, cesium is 376. You do see the general trend as we discussed before, as we move from the top to the bottom for each of those groups. And we can also see like helium, almost 2400, drop down to 2100, 1500, and it goes like that. And from top to the bottom, the first ionization energy decreases. The same thing for the halogen families. So it's going to about 1700, 1250, about 1140, 1890, and it's becoming unknown. The reason why it's becoming unknown is becoming too unstable. So that trend holds. Top to the bottom, first ionization energy decreases. And now we're looking at from across the same period, and you can see 1312, and this one shoots up to almost 2400, and this one is lithium is 520, 899, and 800, and you're also following the trend, it generally increases. But one thing you probably noticed between the beryllium and the boron, there's abnormality. So you can actually go to this table and start playing around with it and pick out the general trends. As we said before, top to the bottom, first ionization energy decreases as the size getting bigger. Left to the right, as the size of the element getting smaller, the ionization energy increases. However, there are a couple of what we call inflection points, abnormal points. So then let's go back to the PowerPoint presentation, and we can see generally, this is the general approach. What we do is to analyze the problem. You can take a look at a problem asking about the trends in ionization energy, especially first ionization energy. Identify the trends in the atomic or ionic radius and correlate the ionization energy with the trends in atomic ionic radius. Larger the radius, lower the ionization energy. But the caveat is there are a couple of places you got to be careful about. So plotted here is experimental values for the trends for the first ionization energy of each element plotted against atomic number. As you can see, the trend is increasing. This is the first period, and this is the second period, third period, fourth period, fifth period, sixth period, and the seventh period. As you can see, the general trend holds, but there's a couple of different points I'm going to mention in the next slide. As we come here is the first ionization energy of the element 1 through 20, and you can see from the hydrogen, helium, lithium, beryllium, boron, and all the way to nitrogen and oxygen. So you can see right here the general trend is increasing in first ionization energy across the period, and also the decreasing in first ionization energy down in the same family or same column, family or groups. But what I want to emphasize on are those two places, and sort of the trends is kind of reversed. So this, remember, is group 2. So this is group 13. So this is also group 2 to group 13. So this is group 14 to group 16. So this is group 14. Oh, I'm sorry, this is a mistake, and this is not group 14. This should be group 15. Group 15 to group 16, and this is also group 15 to group 16. Okay? In the following slide, I'm going to explain to you why this is the case, why there's abnormality between the group 2 to group 13 and group 15 to group 16. And let's take a look at the typical group 2, what is the valence electron configuration. And if you can recall, group 2 elements, as you recall, the group 2 elements, it has a valence shell electron configuration of Ns2. Group 13, you have the Ns2np1, and the starting of the next sublevel, the np1, causes it to go to a slightly going up into the np, the pp sublevel. It's more than compensated by the shrinking of the atomic radius. So in this case, and this one, the group 13 has a slightly lower first ionization energy. And the situation between group 15 and 16 is a bit different. So as we say, it's group 15. The valence shell electron configuration, you have NS2, NP3. And more importantly, let's take a look at the orbital notations. And this one will be NS, and this one will be NP. On the NS, you have the paired electrons. On the NP now, you'll have the 3 unpaired electrons. Group 16, you have NS2, NP4. Same thing. Similarly, the orbital notation will be NS, up and down, NP. You have 3 of them. Now the case is up, 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 and the 4th one has to come down to the one of the p orbitals and pair up. And this, let's choose a different color. This is the key difference. As we see before, the electrons, interaction between two electrons, are repulsion, negative and negative. So when we try to force this electron come in, obviously they have to go to the opposite spin direction, but still the negative repulsion still exists, and that makes this group 16 element slightly less stable on its ground state than the group 15. Hence, this one has a slightly lower first ionization energy. Other than this, group 2 to group 3, group 15, group 16, the general trends holds with respect to the correlation between the first ionization energy and the size of the element, or the size of the ion. Let's take a look at some examples. First, let's take a look at the example. Just rank the following elements. In terms of increasing in first ionization energy. What I want you to do is cesium, calcium, magnesium, potassium, rubidium. Okay, so let's analyze the problem first. Remember, the first step in solving any problem is analyzing the problem. What we're asking is the first ionization energy, and we also want increasing. What does this increasing mean? The increasing means you're going from the lowest to the highest. So we want first ionization energy. Then remember the link between the size and the ionization energy. If we want to go from the lowest to the highest, so essentially we want to go from the largest to the smallest. To the largest to the smallest. So now then we can take a look at on the periodic table what do we have. So now you realize cesium, rubidium, potassium is all in group 1, calcium and magnesium group 2. As we know the trends, the cesium is larger than rubidium, rubidium is larger than potassium. And across the same period, calcium will be smaller than potassium, magnesium also will going to be smaller. Now it's in the same group 2, magnesium is going to be smaller than calcium. So then in terms of size, it will be cesium is going to be greater than rubidium, is going to be greater than potassium, potassium is greater than calcium, calcium is greater than magnesium. In terms of ionization energy, first ionization energy, then cesium is going to be smaller, then rubidium is going to be smaller, then potassium is going to be smaller, then calcium is going to be smaller than magnesium. Okay, so when we use this kind of approach, just be careful about the group 2 to group 13, group 15 to group 16. This is where this two abnormality happened. And let's take a look at the last example. Is in general on a periodic table, which element has the lowest first ionization energy, and which one has the highest? Which one has the lowest? Which one has the highest? And let's take a look at the periodic table in general. And as we remembered, in ionization, first ionization energy decreases from top to the bottom and increases from left to the right on the same period. So what we're looking at is the francium should have the lowest first ionization energy, and I can take a look at it. The value is 380 kilojoules per mole, and helium should have the highest first ionization energy because it's the smallest. In this case, it's 2772 kilojoules per mole. So the answer for this particular question is the lowest first ionization energy should have francium, as has the highest should have the helium. This is in general it's connected with the size. It's connected with the size and the general trends of the ionization, first ionization energy. To recap, in this section we discussed about the definition of the ionization energy and the trends associated with ionization energy and the correlation between the first ionization energy and atomic radius. And there are a couple of points: the group 2 to group 13, group 15 to group 16, and the trends got reversed. Is actually the group 13 element has slightly lower first ionization energy compared to group 2. Same thing is group 16 element have slightly lower first ionization energy compared to the group 15 elements. With that, you need to have additional practice working on the worksheets. Thank you very much for your attention, and that's the conclusion of this vlogcast.